As promised, I am back with another video on calculating the NMR yield using the internal standard. But in this video, we are going to use the internal standard after the reaction workup. And in the previous video, we used the internal standard during the course of the reaction. This method, which we are going to discuss today, is very useful because it has several advantages, and this is the most commonly used method by the chemist or the researchers. So the first advantage is that this method can be applicable for the reaction which are performing in the harsh reaction condition because there is no risk of decomposition of the internal standard. Second is that you are adding the internal standard only in the aliquot of the crude reaction mixture. So this way you are protecting the remaining amount of the reaction mixture from the contamination by the internal standard, and this is especially useful when you want to purify your product by flash chromatography. And the third advantage is that you are using the milligram of the internal standard only. In the previous method, you need to add equivalent amount of the internal standard, and which could be higher according to the amount of the starting material. So therefore this is economical and convenient. So as we will go through this video, you will understand all the advantages and disadvantages of this method. But I would like to highlight one point: we cannot use this method to calculating the conversion of the reaction. This method will be used only for calculating the NMR yield of the reaction. So let's start this video.
We are going to understand this method step by step. So the first step, just prepare your reaction as usual. Note down the millimoles of the limiting reagents. I am taking the amide coupling reaction, and where the benzoic acid is the limiting reagent, and the scale is 2 gram, which has 16.37 millimoles, and this is the molecular weight of the product. Okay, now we are not adding any internal standard at this point. The step 2 is do the workup. So quench the reaction. After finishing the reaction, you can quench your reaction, extract with the organic solvent, wash the organic solvent with water, and then you can dry the organic solvent over sodium sulfate, and then collect the organic layer and dry under reduced pressure, or we can say rotavapor, till the dryness. And after that, the third step, to weigh the crude mixture. It is very important to know the amount of the crude in the flask. So let's say this is 2.5 gram. After evaporation, we have crude mixture 2.5 gram. Then you have to take known amount of this crude mixture. So let's say we took 2.7 milligram of this crude reaction mixture in a HPLC wire, and we are assuming that this portion representing the whole reaction mixture, we are assuming that this is the homogeneous solution. Okay, so the homogeneous solution, so we are assuming that this crude mixture is also homogeneous, and any portion you are taking from this flask is representing the whole reaction mixtures. The fifth step is to add the internal standard. You have to add precisely known amount of the internal standard into the same vial. Why in the same vial? Because if you take into the another vial, then you while transferring, you may left some amount of the internal standard, and this will give the error. So therefore you have to add the internal standard in the same vial. I have added 2.5 milligram of the internal standard, which is mesitylene. Then you have to prepare the sample. For preparing the sample, dissolve the residue in titerated solvent. It could be DMSO. If you see in this picture, this is not homogeneous solution, so you have to make the homogeneous solution. Then after making the homogeneous solution, you can assume that internal standard and the crude reaction mixtures completely solubilize, and it is a homogeneous solution. After that, you can transfer into the NMR tube. During transferring in the NMR tube, you may see that few drops or one drop left inside the vial. It is completely fine, because the most important thing, product and internal standard ratio is preserved if the solution was homogeneous. That's why it is important to take internal standard directly into the same vial. Okay, so now you have internal standard in the solution of the crude mixture. So this is the homogeneous solution. If you left one drop, two drops, it means internal standard also left over there, right? So the product internal standard ratio will remain the same when you will do the calculation in the NMR. Okay, so now let's move further. The next step is to acquire the 1H NMR. As I told in my previous video, why normal 1H NMR is not important. The qNMR is very important because it has a long relaxation delay, and when you go to run the NMR, you can find something like that, and proton qNMR modes, and these are like 1H64 scans, and these fast 8 scans. These are normal 1H NMR, and which has short relaxation delay. If you do normal 1H NMR, then you may have error in the quantification of the yield of the reaction mixtures. So let's say this is the NMR of the sample, and now the next step, we have to choose the well resolved non-overlapping peaks of the product and the internal standard. So this is the uh, peak, internal standard peak, and this is also belongs to the internal standard of methyl, and this is from the benzene ring. This part coming from the this ethyl part of this amide, and this is the aromatic part of this benzene ring. Now as you can see that this is actually 1H NMR simulation, that's why you are seeing very well resolved signals, but in the actual you may see some overlapping. So therefore you have to choose only the well resolved non-overlapping peaks. Now I have integrated the internal standard peak to 3, so then another peak should be 9. So if it is 9, then it clearly indicates that there is no overlapping of peak with the internal standard. And after that, integration of the product signal, let's say it is 2.5, and actually it corresponds to 4 hydrogens. Now we are going to use this formula which we have already seen. How this formula comes, I have explained in my previous video. You can watch that video to understand the basic behind this formula. And where N is the number of moles of the product, capital N is the number of protons corresponding to the to that signal, and IS stand for the number of moles of the internal standard, and capital N IS stand for the number of protons corresponding to the chosen peak of the internal standard. And we know that internal standard millimole is 2.5 milligram, so which correspond to 0.0208 millimole. Now you can put these values, 2.5 divided by 4 because it corresponds to the 4 hydrogen, 3, this internal standard integration is 3 and it corresponds to 3 hydrogens, and this is the millimoles of the internal standard. It is very important to note down that we are getting the product millimoles in the aliquot, not of the whole crude mixtures. Okay, so which is 0.013 millimole. You can multiply these millimoles with the molecular weight of the product, and you will get the amount which is present in the NMR tube, which is 2.304 milligram of the product is present in the NMR tube, not in the whole crude mixture. Okay, now we are going to do the scaling to see how much amount of the product present in the 2.5 gram of the crude. Now you have to just do the mathematics. Product in 2.7 milligram of crude is equal to 2.304. So in 1 milligram is this much, and 2500 milligram of crude, it would be this 2.133 gram. Okay, so this is the amount of the product present in the crude reaction mixture. Now we are going to calculate the NMR yield using any one of the formula. So here you are using the moles of the product and moles of the limiting reagent, and in this case you are using the observed NMR yield and theoretical yield in the gram. So I am going to use this equation. In the previous video I used this equation, so in this video I am going to use these equations because I have value in milligram. So the NMR yield would be this 2.903. This is a theoretical yield of this reaction. You can calculate the theoretical yield, which is 2.903 gram, and the observed NMR yield is 2.133 gram. Multiply by 100, which is equal to 73%. So the NMR yield for this reaction is 73%.
Okay, so this was the most commonly used method to calculate the NMR yield of the reaction. But some chemists alternatively used another approach also. What they do, they are adding internal standard in the crude reaction mixture after the workup. So in that case, you need to add, let's say, if the scale of the reaction was 2 grams, so you are adding almost the same millimoles of the internal standard, so it could be more than 2 gram of the internal standard, and then again redissolving by adding the suitable organic solvent and evaporating over the rotavapor. After that, you are taking the small amount of the sample which is representing the whole crude reaction mixture. Now whatever the NMR yield you are going to get after the after using all those formulas, that will be directly connected to the whole reaction mixture. So in that case, you are not doing any scaling, but the problem is only you are using a lot of internal standard, and when you will do purification, you have to get rid of that internal standard, and which will take your time as and uh, and more organic solvents during the purifications. Anyway, if you have to calculate the NMR yield for your own reaction, which method would you choose? Adding the internal standard in during the reaction or after the workup? Let me know in the comment box.